Okay, guys, let's get started with the review for the practice exam. Okay, so for the first question, okay, so this question is a common mode rejection ratio kind of issue, and we've encountered it several times. So we first encountered it dealing with like the differential amplifier, and then we're seeing it again with the transistors. So basically. So the basic idea here is we have some type of device. It can be an amplifier, right? It takes two inputs, like V1 and V2, and it has some output you're concerned with right here, and that could be a reference. And if you have an ideal amplifier, recall that you have this this gain, and it's the differential mode gain, and that has to do with the difference between the inputs, right? So that's one case right here. So this is DM, the differential mode gain. Now, you also have this common mode gain as well that sometimes interferes with your signal. And that has to do with the average of the inputs. Right? So recall that. So here's the input due to the common mode. Here's the differential mode input. So we can write it like this. So you have the differential mode, that gain, and then we can call this part right here just VID. And then we have the common mode gain, and then we can write this as VIC, common mode input. And then what we can do is, this is the gain we're most concerned with. So if we were to factor that out in front of that, we'd end up with this plus CM over differential mode gain, that. Right? And this piece right here, we would relate that to the common mode. So this piece right here is equal to 1 over the common mode rejection ratio. Okay? Or you could say the common mode rejection ratio is just the inverse of that. Now, you want this value right here. Okay, so you want this to be very, very small, because you want your output to be really controlled by this and have this common mode have a very small influence on your output. Okay, so that means you want this value to be very small. Well, that's 1 over common mode rejection ratio. So that means you want this to be quite large, because this is just the inverse of that, right? And so that would mean that this right here, if you want this to be large, your gain for this part, you want that to be much, much less than this right here. Okay, so, and typically this is like the magnitude of that absolute value. So in words, your common mode rejection ratio is like a measure of how well your common mode input is rejected from your output. And so you want this to be quite large whenever you're dealing with that. So that's basically the first problem right there. The second problem, So a BJT and FET, those are shown. And it's asking you to determine all ports. Here are all the ports right here. Here's your base, emitter, collector, your gain, drain, and source that are useful for input, and determine all the ports that are useful for the output. Okay, so if you recall here, we okay, so okay, so when we talked about it before, one way to help remember how these things go, you see the arrows right here? We said, if you see the arrows, then those ports that have the direction arrows, those are good for input and or output. Okay, either or. Okay, the base and the gate, they're always good for input, and the collector and drain, they're always good for output. Okay, so you have your outputs here, your inputs here, and these could be inputs or outputs. So on this problem, you would just write, for your input, things that are good for inputs. You have your base, you have your gate, and then the emitter and source are always good in either case. And for the outputs, you would have your collector and drain, and then again your emitter and source are good for outputs too. So these right here, both cases. Okay, so that's for that. Let me see if I can scroll up with this. No, it's not going to let me do it. Okay, for number 3. So is this PMOS circuit useful or not useful, and why? Okay, so for the PMOS circuit, so so this is the input, here's the output. So remember, on a transistor like this is the gate, here's the source, and here's the drain. Okay? Now this input right here is going through, here's the resistance of the input. So here's like your entire source right here. But that input is coming into the drain. So is that is that a useful type of setup for it's going into the drain? Yeah, see, for input, if it goes into the base or the gate, that's fine, or the emitter or source, that's fine. But in this case, since your input is going into the drain, that's not okay. Now, here's the output. That's taken from this. Well, the output's coming from the source, so that's fine, because the source is okay either way. But here's the problem. So that's not going to be very useful. Okay, so in that case, you would say it's not useful, and then you explain why that the drain is not a very useful input port for that. Oh yeah, and by the way, what type of configuration is this? Like, is it a common source, common drain, common gate? Huh? Common gate, right? Here's another one. So the difference between 3 and 4, you see right here? See the arrow? That's the only difference between 3 and 4. The resistors are the same. Okay, so what about this situation? Okay, so here's the drain over here. The drain is connected to the output. So that's okay. Here's this input is going into the source here. And so, yeah, that's fine too. So that one is okay. That's useful because it's set up properly. I can't fit all this. Wait, I've got to shrink this down a little bit. Okay. So for number 5, so BJT circuit and its relations are given by this. So what's given to you are lots of things, and of course you probably don't need all of them, but you have the Q point. So you have the collector current, 4 milliamps, and the collector emitter voltage is 10 volts. You have the current gain, beta 0 is 50. You have the early voltage, VA, 75 volts. These capacitors, C1 and C2, right here, 10 picofarads and 20 picofarads. You have R input, which is 750, not watts. Got to fix that. It's supposed to be ohms, but my symbol got converted to Times Roman. So these are ohms right here. So RB, 100 kilo ohms, RC, 62 kilo ohms, and R3, 100 kilo ohms. So here's the input resistor, RB resistor, RC, and the load right there. Okay, and what you're supposed to do is determine the overall voltage gain, Rn, which is seen right here. Okay, so this is a coupling capacitor right there, and if you did it into it's also given these values right here. So you have the current gain right there. Wait, this is wrong. You see here? I have transconductance right here and here. What's this supposed to be right here? You guys remember? Yeah, this is the thermal voltage. Oh, here it goes. This equation's right. Yeah, so scratch that equation.
So do you want input resistance or voltage gain? If you ask for input resistance, it would, like, it says determine the overall voltage gain Rn.
Yeah.
And R is the resistance, and gain is not resistance as far as I know.
Oh, yeah, so, yeah, this is wrong. Yeah, thanks. Yeah, just get Rn. Yeah, so there are a few typos in this problem. Okay, yeah, so you are supposed to find Rn. Everything else looks good. Okay, so so in this case, what you want to do is let's erase this. Okay, so in this case, you can convert this to your small signal model right here. If you have difficulty in recalling what that looks like. So when you convert that to your small signal model, this right here just connect these right here, common reference. This goes to this situation right here. Where it has some input resistance of the transistor itself. Transconductance and VBE, and here's VBE right here. I'll also put it over here too. Here's VCE, VCE over here. And here's your output resistance. And like we said many times before, sometimes you may want to ignore that because that's usually quite large, but it's in parallel with these other things, so those dominate. But that's what you want to replace it with right here. And it's called the hybrid pi model. Okay, so if we take this piece right here, which is this, and then we substitute this in for it, then you can see that this RB is going to be in parallel with this R pi. Okay, so Rn is going to be your RB in parallel with R pi, and in relationship with R pi, that's useful here, is that your gain here is equal to R pi times your transconductance, and your transconductance is equal to the collector current divided by your thermal voltage. And is everything given to you? Yeah, here's your current gain, that's given to you. IC is given to you. You should know the thermal voltage. Do you guys remember what it is? Yeah, 1 over 40. Yeah, so I think you guys are supposed to know that. So I would like to give it to you, but but it's like one of those things that's like so common that I think you guys are supposed to know. Yeah, but remember it's 1 over 40. So that means that you could write this, and you could probably even remember it like this. Yeah, so that's it for that problem. Yeah, just plug in the numbers. I think that's everything that you need for that. Yeah. Okay, sketch the small signal model for this following BJT circuit. Oh, good. So we'll just leave this up here. They cleaned the board with something, and it's not. Yeah, it's not really racing. The stuff's not really working that well. Okay, so this part right here, here's your transistor. So put a box around it, and that's what we have here. And then just put this in that box. Okay? So that means you're going to end up with a circuit that looks like this. That's grounded. This V in. You have your RI. Here's your RB. Right? Okay, so now we're at the point where we substitute the transistor with this right here. And so we're going to have R pi. And we're going to assume that these are the same reference, right? We could draw a line across that to make it even more clear, but they're at the same reference point. Transconductance and VBE. And this VBE is, here's VB, here's VE down here. Okay. We also have R out. And this just goes to ground. And this other part, oh, that just goes to ground here. the load is connected right there. Yeah. Yeah, so that's all you have to do for that problem. Okay, so for number 7, okay, so you're given the Q point here. You're given the current gain and the transconductance with the differential input resistance, RID. Okay, so this is one of the cases where you are using half circuits, right? So this right here is a small signal model of that, which is kind of funny because you get this. Yeah, so if you weren't looking ahead, you could just use this in your last problem. But anyway, so here's a small signal model, and so what is the differential input is what you're looking for. Okay, in this case, you have two differential signals, and so in half circuits they're just split up in two. But if you put them together, that's what you're really looking at. So VID, half of it's going through this R pi, half's going through that R pi. So really, you have one ID going through two R pi, two of those. So your RID is equal to 2 R pi, and the relationship with R pi, it's a beta relationship, R pi transconductance. Oh, this is like the same kind of problem. Yeah, so it's right here. So, yeah, I'll just write it. Yeah. Yeah, so these are the equations, and all I got to do now is just plug in the numbers, and that's it. So here's the part you really have to recognize. Everything else is just trivial after that. That's the part you want to recognize, because it's in half circuit mode. Okay, so here, here's a, so we have 4 transistors here. You have a FET and 3 BJTs. So you're given this, the voltage between the gain and the source for the 4th transistor. That's this one. So here's Q1, here's Q2, here's Q3, and here's M4. So you're given that. So here's the gate. That's the source. So the voltage here is 2 volts. What is the Q point of the transistor here? Okay, so the Q point for that transistor so we know the Q point is just for Q3 here, is IC, well, in this case, it's the third one, so it's IC3, to not be confused with the other ones, and V EC3. Okay, so you just need to find those to find the Q point. So IC3. Well, okay, so ask yourself this question. How much current is going in here, this direction? Huh? Yeah, yeah. How much is going in that direction right here? Yeah, yeah, 0. So that means this current right here is equal to this current. So that's great. So you can say that this IC3 is just equal to I2. Okay? And now the voltage between the these right here, the emitter and the collector, So what's the voltage right here? We just follow it, and you can see it's just VCC. And this voltage right here, well, we were given what this voltage is right there. So in this case, the voltage, across those two ports is your VCC minus VGS4. Yeah, then you just plug your numbers in. That's the key point. Okay, so what is the dominant pole? Well, the frequency, the high frequency of that pole, for that right there. Okay, so this is like the most recent stuff we've been going over right here, where we realize that we could take these gains and break it up into a mid gain, right, multiplied by two factors, where you have a low frequency factor and a high frequency factor. And the thing was that, yes, let me scoot this over a little bit. So that's a constant. Okay, this is a constant. This right here is a function of frequency. This right here is a function of frequency. And so this right here is a function of frequency. And this is what, you would do your Bode plot with this. But that is a constant. Okay, so you can take any of these transfer functions and break it up into these factors. Okay, and the key to these factors right here are that this piece right here, when omega gets very high, this part right here goes to 1. So really, if you're just looking at high frequencies, you could just cover that up, get rid of that, and these are the two factors you're really concerned with, because that just becomes 1. Or if you're looking at low frequencies, this piece right here becomes 1, and then you can just write it like that. Okay, but this is like the full expression. Okay. So we're looking at the high frequency here. So, and also this too. How to tell? Okay, I'll write those parts generally. Okay, so for the low frequency stuff, it looks like this. It's in this form, where you have your Z's on top. And they keep going. And then you have your poles on the bottom. And you have maybe possible other factors. That's the form of FL. The form of FH, the high frequency ones, you rewrite them like this. And these are the zeros. And they keep going, divided by this. And clearly you can see they're interchangeable in form, right? But so how do you tell which form to write it in is the question. And that is determined by, the size of that frequency, right? So the components that have really high frequencies, you write them like this, and the components that have low frequencies, you just write them like that. And that's how you're able to break apart your factors, okay? And another thing you probably have noticed by now is that this part that comes out is a combination of whatever factor is already there multiplied by any other factor you use to get this, right? So in order to make these right here, you have to get the s by itself, and whatever it's added to becomes this. But if it took some kind of factor to do that, that comes out and gets multiplied by this. Same thing here, right? If you're like this, but it's a high frequency, you have to convert it to this. What you want to do is divide this away. That becomes 1, but this becomes s over whatever that is, right? But then that factor you used comes out, and it becomes part of A mid. Okay. So in this case right here, we are not starting off with any other factor. So in this case, it's starting as 1 in front. So that's going to be, our A mid starts as 1. But we're going to convert this to high and low components, right? And we're going to see what comes out, which is going to be multiplied by that. Okay, so in our case right here, we have our AV. Well, the interesting thing here is that if you look at all the frequencies, they're all pretty high, right? Okay, so so let's do the pole. So let's do the numerator first. So the numerator, yeah. So since they're always high, then we'll do it like this. So this numerator will be converted to this right here. Okay, and that's like omega z, omega hz. That part on the bottom with the 4 times 10 to the 6, we'll write it like this. Okay, and this other part is already in the form we want it, so let's leave it. Okay, now in doing this and this, we had changed a few things, right? We didn't have to do anything here. But for this, we basically pulled out part of AV. So let's move this over here. So to make that, we had this factor. Right, so if this went back in there, then it would turn back into that. And for this piece right here, we had to deal with this factor right here. And so if we multiplied this back into one of these, this would turn in back to that. We didn't do anything here, so that is not contributing to the A mid. So this is A mid. All this right here corresponds to our FH. And we don't have anything that's like really low frequency stuff. Okay, so now the question is the dominant pole. Okay, so we have 2 poles here, right? The dominant pole in this particular case is going to be this one, because this occurs first before that one. Okay, so here's our dominant pole. So in this case, you would say omega h is like 4 times 10 to the 6 radians per second. Okay. Yes. Oh yeah, yeah. Yeah, it's like let's give like a basic example of like, something that would be like some A mid, and then you'd have some other things that fall off. So you would have, this right here, may do something else. Same over here. So these are dominant poles right here that you're really concerned about. Okay, so this will be your dominant pole for H, for omega H. This will be your dominant pole for omega L. Because typically, you're concerned about this region, and that's the region where you're saying, hey, well, here's like the bandwidth, right? Even though you have these other omega H's out there, but that's your dominant. If we asked you to find what?
Find it for omega L instead of omega H.
Oh, yeah, yeah. Well, yeah, so in this case, not this problem, but if there was like another problem where we're looking for omega L, yeah, it would be this one right here. That's exactly right. Even though you would see these other ones in there, you would pick that one right there. Okay, so number 10. Okay, so this is similar, right? Now in this problem, it has more terms, but that one is asking you, well, what is this piece right here after you converted it to something like that? Okay, so let's do that over here. Okay, so if you look at the frequencies here that can come out of this, here is kind of clear that this contains both this factor and this factor, right? Can you guys see that in there? Because you have like some low number terms, like you have a 2 and a 3. And then you have these higher terms right here that's going to act as your zeros and poles. And so you can imagine two separate parts of that, where you can have an A mid, you could have a factor that plays the role of FL, and another factor that plays the role of FH. So we'll write it in that form. Okay? So we'll put our A mid on back because we don't know what that's going to be yet. But for our FL, here's our FL right here. That's going to be, first in numerator, we have that S plus 2. On denominator, we have our S plus 3. And as you can see here, it's in the right form already, which is good. So we didn't have to convert anything. But sometimes you do have to convert that. If you have to convert that, any conversion you do will contribute to A mid. Okay? Because then you have this factor you got to pull out in front. Now so this right here is our FL. Now the next one is going to be our FH. Well, we have to get it into this form right here for our FH. So we have that 400. So we're going to have 1 plus S over 400. We also have the 100. So 1 plus S over 100. I'm going to put the factors out in a second. And then we have on denominator S plus, oops, I'll just write it this way, S over 200 is 1, but this is cubed, right? So in this case, we had to do wait a minute, everything did conversions for everything. So we have a 400, we have a 100, and we have this 200 cubed. And you can clearly see that if we put these 400 and the 100 back in here, we'll get that back. And for this right here, it's like a third order pole. is just, basically 3 of these. Right? So you're dealing with that. So that's why you have these 3 200s, and then you can put each one back in there and get that back. Okay, so in this case, this right here is our FH, and this right here is our A mid. Okay. Yeah. Okay, so what is the total input capacitance of the circuit? So remember that effect for the total input capacitance? Remember like the name of that? The Miller effect? So for the Miller effect, so one way to think about this is, here's your input. So basically your input is an RC circuit, R and C, right? And it's being fed in to this whole thing right here. Okay? Now, to do good separation, that's one use for the Miller effect. And even though you have this capacitor here, one good way to deal with that is to put this capacitor in parallel. And the Miller effect helps you determine how to put that capacitor in parallel, and it was called the effective capacitor, or C effective, right? So basically you have okay, so this piece right here can, how we were introduced to that before, that piece right there looked sort of like this, where you had this I C coming in. You get this amplifier. They have some amplifier, some gain AY. You have this capacitor on the loop. Let's call this CY. Well, in this case, let's call it C mu. Okay? And it continued on. But this is like the input, and you want this to be converted to something that looks like this. Where it is your AY. Here's your C effective right here, our equivalent. You want it to convert to that. And the connection between these two guys right here is that your C equivalent was equal to your CY 1 minus your AY, or in this case is mu. Okay? So this is the Miller effect right here. So your total capacitance is just this capacitor plus this other capacitor here, which is your equivalent capacitor. So that means that your total capacitance is this C, what do we call it? C pi plus your C mu 1 minus AY. And the gain is given to you right here. So in that case, it's equal to C pi plus C mu 1 plus GMRL, like that. Okay. So that's capacitance seen by the input. And last, it's good so we can see it. Okay. So on this problem right here, it says label each amplifier as either common collector, common emitter, common drain, common gate, common source, or common base. And that's all of them. And, oh, I didn't have here useful or not useful, so hopefully they're all useful. So, but even if they're not useful, they could still be one of these. Well, I guess I'm okay. So, okay, so what about this one right here? So you have a gate, source, and drain. Yeah, this is a common source. Yep. And this one right here, gate, source, drain. Yeah, this is also a common source. Okay. There's different polarities, right? This one right here, base, collector, emitter, common emitter. Right here, gate, drain, source. Huh? Yep, this is common drain. You see that right here? This one right here, area base, collector and emitter. Yeah, common collector. And this right here, you have a gate and collector and emitter. Yeah, common gate. Yeah. Yeah, common gate. It's not gate. It's base. Yeah, common base. Yeah, sorry. Okay, yeah, that's it for that. Okay, guys. So that's it for today. I'll see you guys tomorrow.